Okay, welcome everyone to my 9th lecture on quantum topology without topology. Today we will see a lot of diagrams again. I know the previous 2 or maybe 3 lectures were a little bit algebraic in nature. And today we'll come back to have a nice mixture between topology and algebra. And combinatorics, actually. So basically, topology tells you what you want to know, algebra tells you how to approach it, and combinatorics tells, in the end, is the right tool to do all the calculations. So in some sense, the question today is, can we separate? So we have this, as we have seen, we have this zoo of different categories with different notions. It's algebra, right? So for basically any kind of concept you can come up with, you have a huge number of huge families of examples. And kind of the question we would like to ask is, can we separate kind of the topological boring ones from the interesting ones, right? So there are a lot of those categories, and some of them are really good to get the general theory to work, but they might not be really interesting to calculate, let's say, topological invariance using them. It's of course not as easy, right? Life is never as easy as that, but in some sense we can. And yeah, so let's just jump right into it. Basically, after something like 20 minutes, we will see the first diagrammatics, but we will start with a little bit of algebra again. And what I want to discuss is something actually very nice, which took me a while to understand. Also, it's extremely simple, just nobody has pointed it out to me. So let me just do it for you. So I want to know what home spaces look like in well, my favorite type of categories, right? So the ones we discussed in the previous whatever 3, 4, 5 lectures. So where algebra and all those categorical notions come together, like pivotal and braided and whatever. And the motivating example, and everything will be built on this example. It won't be as easy anymore. Obviously, life isn't never easy. But basically, that's what it is. It's matrix calculus. So in some sense, all the algebra I'm doing is a fancy version of matrix calculus. So let me tell you why and where this comes up. So let's say you have a semi-simple category. So this notion was really semi-simple, right? So my notation here was this. K was a kind of ground field, whatever it was, ground ring, and the S was semi-simple. Remember this one here. And for a semi-simple category, the right notion of elements were the simples. So here I have my set of simple modules, L1 up to Lm, whatever, some finite set of simples. And Shor's lemma basically says the following: if I have a simple Li and I have a simple L, let's say J, and I want to know they have a map between them, this was a really bad map, I have a map between them, whatever, F, then there are basically two cases. Let's say K is reasonably whatever K is reasonably algebraically closed field, blah, 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 blah. In most cases, F comes basically in two types. F is either 0 if Li is not Lj, is not equivalent to Lj, or F is well, basically an isomorphism, is a scalar. If Li equals Lj, F could still be 0, of course, but this is kind of it's a boring case I want to ignore. And if Li equals Lj. So there are basically only two cases, right? So either your two simples are equal, then morphisms between them are isomorphisms, or 0. Or they're not equal, and then it's even easier, then the whole home space is just 0. The only morphism is 0 morphism. And this gives us the following really, really cute formula to calculate dimensions and morphism spaces and everything, assuming that we know what the symbols are, of course. So in a semi-simple category, each object is a decomposition of simple modules. And this was just my notation for the simple Li appears with a certain multiplicity. This was a multiplicity. Here's the same. The simple Li appears with a certain multiplicity. And you will see an example on the next slide, so don't worry. And so X and Y come with a certain decomposition. And semi-simplicity and Shor's lemma tells you that the home space between them is now just a matrix algebra in so those guys give you the dimension of the matrix algebra. Okay, and obviously if it's just a matrix algebra, so they're just the maps are just matrices between the objects, the matrix algebra. And of course, then you can calculate the dimension. What is the dimension of a matrix algebra? Well, it's the product of those two guys here, right? So this one and this one. So if you know the multiplicities, you basically know the home spaces. That's what it's written here. So let's do an reasonably explicit example. So let's say X is an object which is this one. It's L1. So here's X, L1 plus L2, and L1 appears twice. And let's say Y is L1 plus L3. And my notation is, of course, that different L's are not equivalent. Right? So L1, L2, L3, those are my symbols. Not equivalent. Okay, and now you want to compute end of X. What do? Well, you write down all the symbols that appear, and kind of each symbol is its own universe. So just you can draw a line in between here, so they don't know each other. So you only have a map from L1 to from L2 to L2, and you have this matrix algebra of maps because you have two copies of L1. So it's easy to see why you have a matrix algebra. Well, from L1, and you have two copies. It's up here, but let me just draw it again. From L1 to L1. So what can you do? You can either go here, or you can go here. So you kind of have a, oh, well, now I have to, well, what, you kind of have a, whatever it is, you have a column in a matrix, or a row, whatever. And you have a second row in your matrix, because from here you can go to here to here. Oh, and probably I just swapped it, and this should be a column and a row. All right. One convention works. The point is you just separate your symbols, and you see the corresponding matrix algebras turning up. So 2 by 2 matrix, because you have two symbols. The only thing that's interesting is this 2 here, and secretly here is of course a 1, and this is this 1 by 1. Home from Y to Y is even easier. You just have your separating line here. L1 can't map to L3, L3 can't map to L1. So it's just two copies of the ground field, so 1 by 1 matrices. If you go from X to Y, it's even easier. So you draw X at the bottom. Here's X. Here's Y. This guy can't go anywhere. It's just separated. This guy can't be hit by anything. It's just separated. And then you just count here this space, and it gives you a certain matrix algebra. So 2 by 1 matrices. Okay, that's how it works. You just write down your symbols in a semi-simple category, and you know what the home spaces are. Just a counting problem, right? It's a counting problem. Write down, it's a counting problem. Look at the size, look at the numbers, and you know what the matrices are. And this case is a bit special here, because Y is then called multiplicity free, and you can see why, because In the multiplicity-free case, home spaces are just direct. So of course, one by one matrices are just the ground field. So it's just direct sum um, of two copies of K, and that's true in the multiplicity case in general. Multiplicity-free case in general. Multiplicity-free just means you have ones everywhere, or zeros. Zero is also perfectly fine, but not a two or three. So we get the boring matrix algebras, namely the one which are one by one matrices, right? Um, and then home spaces are just direct sums of the copy of the ground field. Problem is a little bit it's just wrong um, in the non-semi-simple case. So this fails in the non-semi-simple case. So for a non-semi-simple category, Schur's lemma usually doesn't hold because you would need to look at whatever the indecomposables. Schur's lemma between indecomposables is just wrong. Um, so home spaces don't need to be matrix algebras anymore, but they still have some property. So usually something like a local algebra. So it's kind of the closest approximation to a matrix algebra, if you want. Just be aware that semi-simple is much easier than everything else. Okay, and explicit example is for my running example here. So F4, F5, Z mod 5 and characteristic 5. And you have the simple module, which is indecomposable. You have its projective cover, P of the simple module, which is indecomposable. And by definition, you have a map between them because it's a projective cover. So you have a map, a non-zero map. Right, so Schur's lemma certainly fails in this case. The only thing you basically can still do is you can still have an idempotent decomposition. So that's what you can do. You have an idempotent decomposition, and it looks like, as we've seen before, you just have zillions of those maps and inclusions and projections. We'll do an explicit example in a second. And it depends again on those multiplicities, which I wrote something like x over z. Right? You just have a lot of them. And the maps on the isotopic components are actually unique up to scaling. The other ones are a bit trickier. They're not unique up to scaling. They mix a little bit. They exist, but they're not unique. What is an isotopic component? Well, an isotopic component is, let's go to this example, exactly this part. So you just collect all, so the green and the red, these are the isotopic components of X. And in this case, X is exactly in the same notation as above. It's just 2 times Z1 plus Z2. Z2? Yes, Z2. That's X. And the isotopic components are just collect everything which is isomorphic, right? So this is an isotopic component, the green one, the whole thing, not Z1 and the other copy of Z1. So the Z1 and the other copy of Z1, so the whole beast, not each copy separately. And for Z2, it's a bit boring. It's just what it is. But in general, just collect everything of the same isomorphism class. So what is unique is the projection from, so the combination of those two, basically. So you have choices how those projections look like, and also for the inclusions. But up to scalars, there is no choice for kind of the sum of them. So the projection on the isotopic component, that's what it is. It's unique up to scalars, and that's kind of the best you can hope for. And here it's just boring. I mean, you just have one, but anyway, and they are unique up to scalars. And that's kind of the best you can hope for. So you don't have this nice pattern of just matrix algebras. And in some sense, it's the same. It's just a bit more complicated because now you have z's, and homes between z's are not necessarily trivial. So if you want to write down component maps for each of one of those arrows, then these are, of course, the projection matrices, the idempotents. at least in one direction. So these are the straight arrows, this one, and then you have the. I probably get my rows and columns wrong right now, but it doesn't matter. You will get the point. Right. And this is why you get a matrix algebra. And it's kind of the same here. Just that home spaces are not trivial anymore. It's kind of the best you can just do is this idempotent decomposition. Yeah, so you can write them down explicitly. And the point will be that the colored parts for any morphism have to be 0 in the semi-simple case, but not in the semi-simple case. So just be careful here. Okay, so be careful. So this thing just dies in the semi-simple case, and you really get those. You can see it, right? You can get this decomposition into matrix algebras. One here sitting in the uppermost corner and one sitting in the lowermost corner. And these are exactly the projections that I showed you. And the one on the isotypic components, they are exactly the identity matrices in those components. While these guys here are not necessarily, well, this is the same, of course, but the other ones are not necessarily unique. It's the same here, right? But the point is kind of the mixed morphisms, they don't need to be trivial. Okay, so let's go back to diagrammatics. So what I just showed you is, well, okay, we have idempotents in our categories, so we should include them in the diagrammatics. And that's what I'm going to do. So put idempotent into diagrammatics, and the convention is, well, z is still the arrow pointing upwards from I to I. So we are now in the setup generally just some fiat category with some indecomposables. And the extra morphism that are important are these projection and inclusion morphisms, which I just denote by the corresponding box, and they go from X to I. So X as some I turning up in its component, like here, the I, Z1. And these are the projection and inclusion morphisms, and these are the unique ones, the isotypic ones. They're just a box, and these are the components of the isotypic ones. So in the notation from above, these were those kind of matrices, and those guys here were these guys of matrices, other block matrices. There might be other parts of the whole map, of course, as in the example above here. And yeah, and what you get is exactly the projections inclusion gives you the following diagrammatic equation, 9,4. So X, I have a map from X to I, which is my projection, and I can include it again into X. And the point is, if it takes a sum over all of the isotypic components, I have n of them, then this is just identity, and you get this funny relation here. And vice versa, I can go from I, remember that's just zi, to X by inclusion and project again to I. And you would like to say that this is also just the identity on I, but it isn't quite. It's the identity on I times the multiplicity. So X is the I, and it has to be because these are the kind of the components. This is the second kind of relation. And that's basically the difference. Otherwise, these morphisms behave as you would think they do, like they slide. Here's a sliding. Oh, this was bad sliding. So they slide. They satisfy this kind of relation, so the Reidemeister relation in case it's braided, and so on and so on. So really not too bad. We only add in certain extra boxes for exactly those guys here, the inclusion and projection generator. So these are my extra boxes. Okay. Yes. So very good. So right. So this decomposition here, maybe I shouldn't do it in blue. Maybe I should do it in orange. Say. So this decomposition here, identity sum over isotypic components. That's n sum over the various components of the isotypic component. That's exactly this relation here. So this is orange. Um, I could split this further. I could sum over those things here if you would like to, but yeah, I don't need to. Um, and yeah, and the other formulas together give you those things. Sorry, those things here, right? Because this is the isotypic component. So the isotypic component is a map built out of those guys, and how often do those guys appear exactly with this multiplicity? That's why you get this relation. Anyway, I'm already starting waffling here. So new boxes for inclusion and projections, otherwise same calculus and everything nice. So this is nice, this is nice, as we are used, as but we are used to that right now, right? By now, right? And with such a notation, it's usually easy to revise something like dimensions. And remember, dimensions were circles. So dimensions were circles. So the dimension in a reasonable pivotal category was just a circle. And now I'm kind of considering circles labeled CI, which are basically circles labeled I in my notation. And I haven't told you about traces in additive categories or whatever, in dimensions in additive categories. But the first thing you would need to write down is a lemma like this. Like traces behave additively. Not very surprising. Remember that we're the left and the right trace. That's why the C, so this is the right trace. That's why the C is on the right. And here we have a left trace. That's why the C is on the left. Don't worry about it too much. Remember that for most reasonable categories, left and right is the same. Anyways, the spherical ones. So you basically can ignore the distinction and just think you have a trace. So this, for example, was the left one. Because I'm closing to the left, right? Closing to the left. Anyway, and the same way you have left and right dimension, and they satisfy exactly what you think they are. They do, right? That's what you should be used to for vector spaces. Dimension of it's too trivial for vector spaces. Maybe you never wrote it down for vector space because it's just too trivial. Dimension of v plus w equals dimension of v plus w. Yes, and yeah, and okay, this is just what you write down. Obviously, there's not much to say, and the point is this proposition, which is really nice, and it says in a pivotal whatever, in a pivotal semi-simple category, the simple objects are never of dimension 0, and isomorphisms have never trace 0, which is really a strong property, as we will see in a second. So again, semi-simple is much easier. And of course, if you think of it like, okay, my maps basically look like this. Yeah, okay, trace doesn't look very 0 to me. Right, any kind of morphism is built out of those blocks. And so point is, in a semi-simple categories, dimension never vanish, and that sounds innocent, but it's extremely important. The proof is basically is using Schur's lemma. It's just using Schur's lemma, and that's it. So you use Schur's lemma, and you pull the dimension of the endomorphism. You pull L dual to one side, and you see this is bigger than 0 and whatever. And you would get a different map than the evaluation, which you can't by Schussler. Proof is not very exciting. It's actually pretty easy if you write it down. The statement is really good. So dimensions in semi-simple categories never vanish. And the example here, which is extremely explicit example, you should keep in mind that this is absolutely wrong um, in non-semi-simple categories. For example, in our Ruma-Teller-Wald category, so this was the calculus with caps, whatever, those guys, and there was a circle, and there was a circle evaluation, and the circle evaluation was something like this one. Okay, and of course, if I would choose the wrong parameter here, let's say I would choose I in C, my ground field is C, and I would choose I, then this one, it would be minus I to the minus 1. And if you believe me, this calculation, then this is actually 0. So the circle value is already 0. And this is the dimension of the indecomposable object, which is just a dot. So you already found an indecomposable object with dimension 0. And it turns out that the endomorphism space, this guy actually also has dimension 0, so 2 dots also has dimension 0. And how do you see that? Well, dimension of 2 dots is, in this case, just 2 circles. And 1 circle is 0, and so this is definitely 0 by the above. 1 circle is 0, you take it out, so you get 0. And then you take out the other one, and you get 0 as well. So it actually is 0 squared, if you want, which is still very 0. And the way to see this is to identify this endomorphism space with a non-matrix algebra, our good old friend Cx mod x squared, and here's a map. Right? So this guy here is x squared. Why? Well, if you take it and you multiply it by itself, you see a circle in the middle. The circle is 0, so x squared is 0. And you can check that this is an isomorphism. Maybe as a nice exercise, you can actually show in this case that all indecomposables have dimension 0, except the trivial one. So this is a kind of SDG. So the trivial object never has dimension 0; it's always dimension 1. So this example is then as degenerate as possible, right? So any indecomposable object except the trivial one has dimension 0, which is completely the opposite from the semi-simple case. Okay, so this is a very nice example. So be careful with dimensions in non-semi-simple categories. And actually, there's a proposition that says for whatever certain types of categories, the following is equivalent. It's semi-simple and different things. Basically, it's semi-simple and dimensions of projective objects are non-zero. That's equivalent. So, and these are just different ways of phrasing it, right? You see it. Yeah. First of all, you have a difference between left and right. There is no, I mean, those just can give you different numbers, but there is no conceptual difference between left and right. You can ignore that. And the difference between those two statements and those two statements is just that one of them is stated for all projective indecomposables, and the other one is stated for all projectives. There's just no difference. I mean, if you know it on projective indecomposables, you know it on all projectives by additivity. And if you know it on all projectives, you know it on all projective decomposables, of course. And that's a pretty strong statement, right? So let me just scroll up a little bit. So a category is semi-simple of a certain type, of a certain kind, if and only if projectives have non-zero dimension. Okay, so that's, and it's not hard to prove. I ignore the proof, but it's not hard. It's not that hard. So this is a really strong statement, right? In the semi-simple case, Any simple object has not zero, is dimension non-zero. In the non-semi-simple case, projectives never have dimension non-zero. They always have dimension zero. Okay. Still, you can say the following. It's a lemma which we need for the following definition. Not really for the following definition, but lemma in the following, that we need in the following. So the dimension of an object x is the sum of the dimension of the simple objects with multiplicities. Them, or left and right, doesn't matter. So here's again the multiplicities, and you take the simple objects. Multiplicities and simple objects. Okay, and the calculation is easy using the rules from before. So whatever left and right. So here is x. You know that x is equal to sum of the corresponding inclusions and projections. So here's I. Now you slide I around. So you take this box and slide it to here. And this, of course, means that the x from here is now sandwiched on the other side. So everything kind of turns around. So this box is this box. And now we can use the multiplicities. So the multiplicities are missing here. This equation. So you would get x over the I. Times, this is just the dimension of I. So only the multiplicities are missing here. Okay, but otherwise the argument is just a sliding argument. And what you would like to do is you would like to have another invariant of a category, and it kind of makes sense to just define it to be the categorical dimension. So the dimension of the category is just the dimension of the squares of the indecomposables, basically. Not quite, because you have left and right, blah, 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 blah. But in the spherical case, it's just really the squares of the dimension of the indecomposable objects. And this really generalizes what we know, right? So categorical dimensions generalize what we know from vector spaces. So from vector spaces, there is just one simple object, and it's of dimension 1. So 1 squared is 1. For Z mod 2, you have to be a little bit careful, but basically what you get is, so because you had two different choices for dimensions, but basically what you get is that the dimension of the Z mod 2 is 2, which is the number of just the number of elements in Z mod 2. And this is what you kind of get in general for those black categories. Here's another one. Z mod 3, you still get the dimension of Z mod 3 is 3. For more general categories, this is not so clear, and you can get basically any kind of crap as a dimension. That's a little bit different than the Frobenius-Perron dimension that we have seen before, although in this case it agrees, because the Frobenius dimension, whatever, the Perron-Frobenius dimension is something that is only concerned about objects and their fusion rules, while this is concerned about morphism, right? You have to be careful with your evaluations and co-evaluations. But otherwise, it's kind of the same idea of numerical invariant associated to a category, and it will satisfy very similar properties. We'll do more examples in a second. So, for example, you could say something like this. In analogy to this one, dimensions of simple objects never vanish in the semi-simple case. In the semi-simple case, you have a fusion category. Remember, fusion was, in particular, it was semi-simple. Then the dimension of the whole category is not 0. And for C, actually, it's bigger, even bigger than 1. You can say something like that. It's a real number bigger than 1. But the point is, it's not 0, right? So dimension is not 0. under the assumption that you have characteristic 0, whatever. And why do you need characteristic 0? Well, you want to take the sum of the dimensions of the simple objects, of which you know that they are not 0. So in characteristic 0, you're of course happy. You just sum them up. In characteristic P, if you take a sum of the same object 5 times, then it's 0. So you have to be a little bit careful with characteristic 0 or not. But otherwise, it's a really nice statement. Dimensions don't vanish in the semi-simple case. Again, this is a really, by the way, really important instance of semi-simplicity, which you use a lot in practice, and it's just not true in the non-semi-simple case, and it's also not true in characteristic, in finite characteristic. Just so in finite characteristic, it's kind of stupid. It's kind of false for stupid reasons, because the dimension of Zmod, the Gmod 2 graded vector space is still 2, but 2 is 0 in a characteristic 2. Okay, whatever. I mean, this is not, yeah, okay. It will vanish for kind of stupid reasons. And the point is, the PF dimension is really about objects, so it's always an element in R greater or equal to 0, while the categorical dimension is about morphism spaces, so it's an element in your underlying field. Okay, so they're not the same, but for complex numbers, they usually, well, they don't need to agree, but they kind of at least live in the same kind of realm. Okay, so second part of this lecture. So let me cut it here, and let me let me summarize what we have seen. So what we have seen is kind of diagrammatic calculus, including the indecomposable object or the simple objects, whatever you want. And the only difference was that you needed to include this projection, and you needed to include the projections and inclusion morphisms. And yes, and that was basically it. And then we were able to define something like a categorical dimension and categorical dimensions. That's the whole point. They were defined as closing diagrams, right? So this guy's here. And it turns out that they are not 0 in the semi-simple case, but they are usually 0 in the non-semi-simple case. And they're actually pretty much 0 on projectors, as the above position is shown. Okay, but let's do something more topological in nature. I would like to explain a little bit about the Alexander Markov theorem, because I want now to take traces in categories associated to topology. And the only thing we need to recall is that there was a category Q sum, the symmetric, the quantum symmetric guys. So that these were where you had crossings, and you can map it to the oriented Brouwer algebra, quantum Brouwer algebra, by just sending crossings to things that point upwards. Okay, it's a very silly map. So you send crossings. Oh gosh, this is the wrong way around. So let me reorder this. You just send crossings to crossings. Okay. To send crossings to crossings, but just put in some orientation. And there's something that's called the Markov quotient. Okay, so this is kind of okay. That's not the Alexander factor. I just call it the Alexander factor. That's not quite what we want. What we want is the following quotient. There's a quotient of this category. I call it the Markov quotient, and it's just this thing modulo the Markov moves mm. And what it is, here it is. So formally, it's the monoidal category is spanned by a certain object and morphisms, as we've seen it before. Very easy. You have objects. It's still the symmetric. Uh, as a quantum symmetric group. So objects are just those guys, and morphisms is just a crossing, and the relations are just the Reidemeister moves. Oops. So these are R relations. And then I have extra relations that are the Markov moves, and they look as follows. Um, so the first Markov move says whenever you have a diagram at the bottom and you have a diagram at the top, then you could swap order. So let me do this. So let's say you have a green diagram at the bottom and a red diagram at the top. Then it's equal to having the green diagram, no matter what they are, having the green diagram at the top and having the red diagram at the bottom. And then you have this slightly funny looking relation, which basically says if there is a crossing stuck in between two boxes, and boxes just are random, not random, but any kind of morphism, then you can just remove it. Okay. And yeah, those are the Markov relations, so the Markov moves. This is Markov move, whatever, those two Markov moves. Okay. And it might be a bit weird why we would like to do that, but maybe let's look at some topology and then we will see what's going on. But first of all, before we do an example, let's do the Alexander Markov theorem. So there's of course the quotient factor m, which is, I mean, wait, of course there's a quotient factor, right? There's the category on the right hand side has just more relations. And the point is, the factor a is fully faithful. Okay, that's not so exciting. That's kind of clear. That's, yeah, that checks. The factor a gives a surjection. That's more interesting. From you take all symmetric groups for all n together, and it surjects into endomorphisms of the oriented quantum Brauer category by taking trace. So we have a diagram in the symmetric group nonsense, whatever it is. You put it in a box and you take the trace. And as we will see below, there's a nice diagrammatic way of doing it. It's basically this operation. And the point is, this is full. It is a surjection. Okay. So basically what it's saying is any kind of link turns up as a closure of an element of Q sub. Any kind of link turns up as a closure of a braid. And even better, and that's why we wanted to consider those funny Markov moves, if you quotient by the Markov moves, and you would do the same trick, just not take the Alexander factor directly, then you would kind of get an equivalence of categories. So again, now we have an equivalence or a bijection, whatever. And this just means, so this in words just says any braid appears, so any element appears, any braid appears in the language that I will see you show in a second. And this says B equivalent to B prime if and only if Reidemeister moves or Markov moves. So if and only if you can go from one to the other by Reidemeister moves or by Markov moves. And oh yeah, and this is a really nice theorem. It allows us to do, well, to again use algebra to do topology, because what it says is here, yeah, I write it down again. Every link arises as a closure of a braid. And the third part gives the precise condition on when two closures represent the same link, right? They're equivalent if and only if you can use Rademacher moves or Markov moves. And this is exactly the right way of illustrating it. So you take, so this is an element of QSIM by definition. And the Alexander closure just takes this element, here it is, sits in this little box, and it closes it, let's say, to the right, if you take a right closure. And if you stay carefully at this example, you will see that this is, for example, the Hopf link. Yeah. And the surprising result really due to Alexander is that every link can be arranged such that it has a purely upwards oriented and purely downwards oriented part. That's exactly what this link is, right? So if you slice this link here, everything points upwards, and here everything points downwards. And if you basically know that result, then you can reformulate everything like I did above. Like every link is a closure of a braid. And in this picture, the Markov moves are kind of quite obvious. So this box sliding move is just you take your box and you slide it around because now it's closed, right? It ends up here, starts here. This is an even easier thing because if you close it, what you will see here is the Rider Master 1 move, and you just kick it away. You just uh, remove it. And the real point is, the real meat is that the real meat is that these are the only relations you ever need. Of course, they hold. That's easy to see. I just illustrated them. But the point is, these are the only relations that we will ever need in this framework, and that's a really strong statement. So that's why it's called the Alexander Markov theorem. Very important. Alexander says every link arises as a closure of a braid. Markov gives you a precise condition to check whether those things are equivalent without going ever to the closure, right? Just checking it on braids, on QSIM. Remember that QSIM was my category of braids. And of course, nowadays we know that there are various cousins of the same thing. Anyway, so what I want to do now is I want to define an invariant using this trick. I want to define invariants of uh, links using braids. And we understand braids. Braids is a nice category. This is a QSIP category. And all I want to do is the following. So I fix my target category, which is some kind of reasonable category. So reasonable braided category. And you can color everything by a chosen object in your category. And this just works as follows. You send your generating object of sum to X, and you send the generating morphisms to the corresponding braiding. Okay. And this depends on my choice X, of course. So I have a bunch of those functors. And you can do this, of course, also in the oriented Bauer setup. Whenever you have a dual, like a pivotal braided category, you just do exactly the same thing. So all that is happening here is I color my strings with a chosen object. That's it. Nothing fancy. And you get the images are usually called something like colored braids or colored tangles or colored oriented tangles, or Anyway, okay. So remember that what we wanted to do is we wanted to distinguish the topologically interesting categories from the boring ones. And basically what you do is, well, you have this notions of categories. So for a braided category, Um, so a fiat category which is also braided is as this notation. This was a capital B. Um, a semi-simple category which is also braided and also a capital B, but I call it MO at the end because it's what people call a modular category or a pre-modular category or whatever. Um, and there's a certain hierarchy that I'm not going into details, but let's so in particular you just need to be careful that the literature is not really consistent what they call modular or braided fiat or whatever. So we'll just be careful. We already know a lot of examples. So vector spaces is everything as usual. Um, uh, for a finite group, this category of graded vector spaces, group graded vector spaces, can only be B modular. That was braided plus semi-simple, basically, right? Okay, let me just go back. So B fiat is braided in fiat, and B modular is basically braided in semi-simple. And it can only be braided if G is a finite abelian group, right? If it's abelian, and but if that's satisfied, it's always fine. Mm. On contrast, this category finite dimensional representations of a group is always good. Um, and in general, um, kind of this category wants to be fiat. Not always. Remember, we need to find a number of indecomposable objects in the non-semi-simple case, but basically you can think of it like an example of fiat category. So the distinction here is the distinction between non-semi-simple and semi-simple. Mhm. So, but I have everything else is in place. I have pivotal, I have braided now, I have finitely many, whatever, I have additive and everything. The difference is one of them is semi-simple and one of them is not semi-simple. And I do some examples here. And I'm not talking about ribbon or whatever, because this is kind of a trickier thing. And I do an example here, how it works for ZMAT 3. You can read it, and it really depends on the choice of your co-evaluation maps, and you might be off by some scalars and whatever. So ribbon is tricky, and I kind of want to ignore ribbon for now. So they are ribbon up to a certain scalar. They're usually ribbon up to a scalar. So for all of these categories, what is usually a little bit tricky as a randomizer, one moves. They usually only hold up to a scalar. That's pity. It's annoying, and we don't like it, and I'm going to ignore it a little bit. But in the end of the day, you just read this example. It's obvious why it's wrong. Just keep in mind that randomizer one moves are a little bit weird in those categories because the only thing I've told you so far that it is braided and pivotal. So randomizer 2 and 3 they hold because it's braided. Pivotal means zigzag and so on holds. But I never had anything about ribbon, which is a compatibility condition between cups and braidings. And this is, as I said, a bit tricky. So let's ignore it for now. Let's rather do something different. Let's as I said, I want to color things in this setup with indecomposable objects. For instance, I would like to write down something like this. So the double braiding and the trace of the double braiding is a colored Hopf link, which is under my assumption here that the endomorphism is just some linear thing, some ground ring thing will be an element of my ground ring. And what you then can do is you can write down this matrix. So I have n indecomposables, the 1 up to the n. So I can write down a matrix given by the values of those guys as entries. But they're all scalars in my ground field, I can write down this matrix. Yeah. So as an example, if a braiding is symmetric, then you can undo the thing here, just straightens out. You get the product of the dimensions. For example, for a symmetric category, the entry of the S matrix or the product of the dimensions. And yeah, well, in general, the S matrix should kind of measure how braided your category is, right? So this is kind of the extreme case where the braiding is trivial, and this should be kind of a measurement um, how far those two cases are apart. So in general, you would expect some nice matrix with some nice properties. I will tell you in a little bit what I mean by nice properties. Um, um, for example, you can do vec g for small g, and I leave it to you to write down the corresponding S matrices, but they basically look as follows. Depending on your two choices, you get the dimensions, and the dimensions are either plus or minus one, depending on the choices, and this is how the S matrix look like. What you observe here is no matter what you do, this matrix is degenerate. Similarly, for the ZMod 3 example, which I did here in all details, you can read it carefully as usual, right? I haven't said that, but as usual, the link to the file is in the description. And this is how it looks like. And if you do some more examples, you still realize, this thing is very often degenerate. Its determinant is zero. In this example, I did finite dimensional modules of S3, a symmetric group with three letters. It had three indecomposable elements or three simple elements. And this is how the S matrix looks like. And it's still degenerate. Whatever, whatever, whatever you, there's almost nothing you can do. So in all of these examples, calculate the S matrix, and all of them give you that the S matrix is degenerate. And if you really want to, that's what we want to do. If you really want to think of the S matrix as being kind of a measure, a numerical invariant telling you how good your category is for a topology, and dimension, it being degenerate is a really bad property. So these categories are not really good for topology, and they shouldn't be, because all of them are in a reasonable way very close to being symmetric, and symmetric categories have this identity, right? So they shouldn't be very good in distinguishing any kind of topological objects like links or moths. And this is kind of comes close to this. So this is, in some sense, what you should expect. Interesting categories like the Valindi categories from that we've seen last time, they have determinant of the S matrix not being zero. We'll see that later. And they're then really good to construct link invariants. Okay, I tell you here how to compute the S entry for categories, and they give you a diagrammatic proof of how it works. And basically, that's why I call it coloring, because you really color your link with the indecomposable object, and you can actually use colors. Anyway, and so let me instead of discussing this proof, this lemma, this is not so exciting. Let me discuss this lemma. So for any such category, the S matrix is symmetric, and that's not quite clear, right? Because it's this picture for J on the inside and I on the outside, and transposing it would put I on the inside and J on the outside, and it's not quite clear why they should be symmetric. But the diagrammatic argument is actually pretty easy. So here I have my two colors. One of them is whatever, red. The other one is green. And I want to go here where green is in the middle. and red is on the outside. And if those two would be equal, then that's what is called symmetric, right? And here's the diagrammatic proof. It's pretty easy. You pull the red string over the green string. Basically, that's what you do, and rearrange everything, right? And the only thing I want to stress, so it's a very easy diagrammatic argument. You can literally see it. The only thing I want to stress here is that really this coloring procedure should be thought of, you color your strings, because, okay, I usually write Z1 up to Zn, and that's probably smarter because n could be 5 million, and I just don't know 5 million different colors. But it's totally fine to think of it like you color your strings with actual colors, like red and green, or whatever, blue and purple. You get the point. Um, and as I said, usually in um, in the setup, the Reidemeister one move only holds up to a scalar, and you can't really control the scalar. The scalar can be anything. The only thing you basically can say is that the scalar is invertible. Okay. That's what you can say. So scalar is invertible. So Reidemeister, I say it again, Reidemeister one is a bit weird, right? Might fail. And you might, it's not so bad. It fails up to a scalar, which usually means you can rescale it. But you just need to be always careful about Reidemeister 3. Reidemeister 3 is a bit, it's a little bit like the small bad brother of Reidemeister 2 and 3. It usually behaves not as nice as Reidemeister 2 and 3. Anyway, let's forget that. Let's just keep it, not forget it, but keep it in mind, but don't worry about it too much. It's a scalar, so you can usually rescale things. Here I'm doing some numerics, not so important. There's something called the delta value, and this defined as this sum. It gives you some nice description of the scalars and so on. Not so important, you can read it. It's just basically this lemma, and we use it a little bit later. Some diagrammatically nice expression, and there's a right version where you put the king on the right, and there's a left version, so here's the king, right? And there's a left version where you put where you king to the right, and there's a left version where you king to the left, and you just take basically the delta is basically wants to be the sum of dimension squares, as you can see, but not quite. It is dimension squares, and you can see it here. It has those funny Reidemeister scalars turning up, maybe with inverses, maybe without inverses for the right and the left version. But it's basically the sum of dimension squares, whatever. Okay, so let's discuss modular categories. Now that's the final thing I want to do, basically. So this is kind of the crucial thing. That's something we don't like. So we really do not like that, because it's kind of saying that the braiding is trivial. So let's see how we can distinguish things. And the definition is, if S is invertible, then whatever, then we are happy. And so then we call it modular. If it's semi-simple plus invertible S matrix is modular. And they're denoted by mocat, for example. And if I don't have semi-simplicity, I would use this notation. And the only exception is, of course, the vect k, because in vect k, this is your S matrix, and it's very invertible. As soon as you get to vect g for bigger g, is almost never it's almost never modular. It's very, very rarely modular. You see it here, right? The point is the S matrix almost always 0. Similarly, for something like finite groups, and it's basically not modular. It's modular if and only if uh, it's only modular if G is a trivial group, and that's again this case, of course. So this is not very exciting, right? We define the notion of being modular of an S matrix to be invertible, and the S matrix basically captures how the writing works. And it turns out that all the easy examples fail that test or just completely trivial, like vector spaces. But the point is, um, so the Berlin categories are modular. They are all modular. And they give really good link invariance, while link invariance cooked up from something like graded vector spaces, usually they're not really good. Okay, so this is the key example, right? The key example is modular is kind of the right notion to distinguish the boring categories from the boring categories, topologically boring categories from the topologically interesting ones. It's kind of all hidden in this invertibility of the S matrix, right? Because the S matrix, I say it again, is just the kind of the measure for the braiding to be non-trivial. Okay, good. Um, so a category which is reasonably interesting is modular if and only if uh, the the unit is the only indecomposable object which braids trivially with everything. So I only wrote down here that it braids trivially. It's so-called transparent. It braids trivially. Okay. So in the modular category, well, you certainly have the unit object braids trivially, and it's the only one, the only indecomposable object, which just means all objects that braid trivially are just direct sums of the trivial object. And this is kind of as good as it gets, right? That's why this is interesting. Okay, so let's talk a little bit about Rumour-Taylor-Wald categories, and I want to kind of check when they are modular. And I claim the following. So the Rumour-Taylor-Wald categories, we call it, they're those guys, right? Quantum, whatever was quantum 2 in this notation, or minus quantum 2. And what I'm using here is just the notation for the quantum numbers, and this is just quantum 2, for example, is just Q plus Q inverse. Quantum 3 is whatever it is. What was that? Is Q squared plus 1 plus Q to the minus 2. So the rule is pretty easy. You look here, you take 1 off, and then you go in steps of 2 until the total number is again this one. In particular, specializing Q to 1 is just, you get quantum. So quantum 3 is 3 for Q equals 1. It's kind of a finer version of writing 3. And the quantum will distinguish links. That's basically the idea. But you should be careful that this really depends on the choice of Q, of course, as I've written it down here. So for Q equals 1, quantum 1 is 1, quantum 2 is 2, quantum 3 is 3, quantum 4 is 4. Yeah, okay, you get the pattern. Quantum 8 is 8. And depending on your different choices of roots of unity, you can have a look at this table. You really get completely different answers. For example, here, the fifth root of unity, quantum 7 is something like that. Could happen. And that's kind of the power of those quantum numbers. You should think of it like it's a polynomial in Q. And for Q equals 1, it's just the usual number. And for any other value of Q, it can be any other value, basically. And what you then would write down is, so let's say Q is not a second or a third primitive root of unity. complex primitive utility. Why you don't want that is because you can look at this table. In this case, quantum 2 would vanish. So this is what is it? Q squared equals 1. And this is the case q cubed equals 1. And in those cases, quantum 2 vanish and quantum 3 vanish. That's what I don't want, because I will write them in the denominator. I have a quantum 2 here and I have a quantum 3 here, for example. And I can write down those expressions, which are called the Jones-Wenzel idempotents. And we will revise them next time. For now, whatever, I just write down the first three of them. Jones-Wenzel 0, Jones-Wenzel 1 is just, so Jones-Wenzel 0 is just empty, Jones-Wenzel 1 is just one strand, Jones-Wenzel 2 is this expression. And that's why I don't want quantum 2 to be 0. And Jones-Wenzel 3 has those 5 diagrams turning up here, whatever. And what I would like you to do in the exercise is I would like you to calculate the traces of those guys. And it turns out that they are just the quantum numbers up to a sign. So quantum trace of quantum Jones-Wenzel I is quantum I plus 1. So trace of Jones-Wenzel 2 is 3, right? 2, 3, up to a sign. And this is how you do the calculation. Just close the diagrams and calculate. It's pretty nice, pretty easy. I've done the other one as well. Just try to do the calculations yourself. It's really nice. It's combinatorics, and as I said, it just play with diagrams. The point is the Jones-Wenzel projectors, the Jones-Wenzel idempotents, whatever you want to call them. They are idempotents, okay? And they will be the kind of the idempotents that pick out the indecomposable sums. Okay. And what I define here is the following. So you can write down those idempotents, you can play around a little bit around with them. And I want Q now to be a primitive fourth root of unity. Okay, so this includes, I have this diagram checks, this diagram checks, this diagram checks, this diagram checks. Why? Because I'm not in this now in this case, and those two are non-zero, but aha, the next one is 0. So the point is a little bit the next Jones-Wenzel idempotent, which I haven't written down, which I will do next time. That's tricky because in this case, you would like to divide by quantum 4, but you can't because quantum 4 is 0. So what you do is, there is this idempotent. Let's assume existence for now. So assume existence. I will construct the next time, and you just quotient out by this idempotent, and you get a new category, which I just give a 4. So here, because quantum 4 is, I killed quantum 4 if you want in this category. And so very easy, it's a diagrammatic construction. You kill a certain projector. So all of these calculations still make sense, but you killed a certain projector. And it turns out that this category is exactly one of those Verlinde categories from before. Okay, so this is a diagrammatic description of one of the Verlinde categories. And how does it work? Well, it has 3 indecomposable objects. These are exactly the images of the Jones-Wenzel projectors. It's a trivial object. It's the image of the first Jones-Wenzel projector. It's the image of the second Jones-Wenzel projector. And the third one is 0, so it doesn't exist anymore. And those are the simple objects, and I've written down the fusion rules in case you want to check that. And the proof, I really would like you to read the proof. It's diagrammatics. As you can see, it's diagrammatics. You really do diagrammatics, and you calculate the S matrix in the end. Here you go. And you can check that this looks very good, right? Determinant is -8. right? So the determinant is non-degenerate. Just do the proof. It's really really nice. It's diagrammatic in nature. There's not much, well, not much you need to know. You need to do all those calculations, whatever. It's not so bad. Um, but the S matrix is of the S matrix has determinant on zero. It's non-degenerate. This is how it looks like. Whatever. Um, so this actually is a modular category, and it's one of our examples. It's Valinde, the diagrammatic version of the Valinde category, which is pretty awesome, I think. Okay. I will, well, okay. In you can do the same in general for any k bigger than we will see this next time. So for any k bigger than 2, you can those temporally deep quotients are those modular categories coming from Berlin. And the S matrix has those entries. Those are quantum numbers. I will do this next time. More explicitly, because for now I haven't told you what TLK is, but this is basically where we want to go. Okay, so basically what I told you so far, and now I will just wrap up what we already have. Will be some diagram. We are almost done. Most of this is just some formulas, so don't worry too much. But let me wrap up. So this modular was a way. The S matrix basically was a way to distinguish topologically boring categories from topologically interesting categories. And I applied it in the setup of Valinde categories because all the others were kind of boring, like group-graded vector spaces. The other things, they were kind of boring, trivial S matrix. And it turns out that there's a diagrammatic description of that category, which I'm going to explain a little bit next time, which I did here for k equals 4, sorry, for k equals 4. And in this diagrammatic description, you can do honest calculations, as you can see here. It's really not so hard. Okay, maybe let me explain a little bit why those modular categories are the why of modular categories. And then that's kind of the last thing we want to do. So it will be further justified later, of course, but it seems to be falling out a little bit out of the blue. I kind of can imagine why the S matrix is interesting, but there are other funny reasons why modular categories turn up in nature, or well, in connection to interesting mathematics, maybe not in nature. So we have the S matrix. And you have a T matrix, and the T matrix is easy. It's just collecting those scalars. So diagonal matrix collecting those scalars. Those are randomized one scalars. The S and the T matrix. And you also have the C matrix. That's a bit complicated anyway. So you have an so you have an S matrix, you have a T matrix, and you have a C matrix. So the T matrix is just, oh, come on. It's just collecting those scalars. So the S matrix is, this was Hopf. The T matrix is just collecting those Rademaster 1 scalars, so R1. And the C matrix is a little bit, yeah, it's a technical thing. It's so duality defines your bijection on the simple objects, and the C matrix is a corresponding permutation. Right? You might have seen this in various instances. Sometimes things get permuted and you need kind of a permutation matrix to make statements true. they're true up to permutation. And in almost all interesting cases, the C matrix is actually just, oh, in a lot of cases, or at least the cases I would like you to think about for now, is the C matrix is just identities. You can kind of forget it. It's a technical matrix to make things work. So this is kind of the identity. Okay. The crucial players are the S and the T matrix. The C matrix is just whatever it is. And the funny thing is, you get a lot of funny formulas involving those matrices. Very strange. You just write them down. They don't seem to be related at all because this is Hopf, this is right master one. This is kind of the, the duality between the simple objects. And you write down formulas like this, which is, I mean, whatever. S to the fourth is dimension of C squared times the identity, while S squared is dimension of C times the permutation matrix. Something like that. It's kind of weird arithmetic that you can do. And I give you an example how that works. So I encourage you to read the example. There are a lot of numbers. I don't want to explain them. Just read it and try to see whether I have screwed up my calculation. Okay, and the proposition is that you get even more, you get formulas. So for modular categories, you out of the blue you get formulas. Strange formulas involving all the things we have seen before. Here's another weird formula. Um, well, weird in quotation marks, of course. Just to, let's say surprising. Surprising is a better word. So you can express a dimension of the category in terms of the dimension of the simple modules and the structure constants, for example. Funny formula. Again, I give you an example. And the point why everything kind of works is that you have this modular group, and that's why people call it a modular category. So we have the modular group, and let me explain what that is. And this is really where the name comes from. And it all starts with this thing, PGL2C. This is very easy. This is just 2 by 2 matrices with non-vanishing determinant, and you get rid of. So the P is referring that you get rid of, you mod out a sign. You mod out uh, by basically by this matrix. So up to the sign. And this is the following group. So this is the algebraic expression of the group of all Mobius transformations of C. And Mobius transformations were those maps. Of course, this is the same condition as down here. And you can write down very nice pictures of Mobius transformations. So here's the Mobius transformation of C. This is one of the Mobius transformations. And Mobius transformations play an important role in kind of Riemannian geometry and so on. Kind of the first easiest, well, Mobius was a mathematician from the 19th century, so they're pretty old, pretty well established. And this thing is just the algebraic model of the same thing. So you can express Mobius transformations in terms of functions of the complex numbers. So here is C, it's another C. Or you can express Mobius transformations in the language I understand much easier, namely just matrices with a certain condition. And this thing here is called the modular group, which a little bit depending on the literature is either the one I showed you above, this one, or the SL2 version of it, where you just would say this is equal to 1, but you can kind of normalize it. Depends a bit on the literature. Right, oh, here you go. Right. So this is Mobius. It depends a bit on the literature. Either this one or this one is a modular group. And the one we like is actually SL2. SL2. So same thing, but just determinant is 1. And the point is that this thing has a generator and relation presentation. And by now you should like generator and relation presentations. And it looks as follows. It has 2 matrices, S and T. There's an S matrix and there's a T matrix that satisfy those relations. And in coordinates, the S matrix is just this matrix, and the T matrix is just this matrix. So you can see, for example, S to the 4 is 1, right? And you can check the other relation, and this is a generated relation presentation of the modular group, which is this group coming from geometry. And even if I was too quick and you have never seen Mobius transformations before, it doesn't really matter. It really doesn't matter. There is some geometry, and geometry usually ends up in nice geometry usually ends up in nice formulas. Algebra is always a bit random. You never really know what you get, but nice um, nice geometry should end up in nice formulas. And the point is, why is it called modular? Well, because it basically has an action of the modular group. And the way you do it is you send the S matrix to the S matrix. You need to scale it a bit. But anyway, and you send the T matrix to the T matrix. So S T to T. And basically S to S, you need to scale it. But anyway, that doesn't matter so much. So modular, so S and T. So T, remember, let me just remind you, S is Hopf, kind of the value of the Hopf link, and T is the T like twist is this one, some scalar times this one, and you collect the scalars in T. And those two things give you an action of this modular group, which is pretty amazing because the modular group is something that people have studied for 150 years, just connected to nice complex geometry. And then you should expect some really nice behaviors, some algebraic behaviors of those categories. And these were those formulas that I showed you before. Anyways, this was just waffling a little bit to give you a hint where the notion of modular comes from. The takeaway message is modular categories are really good objects. Good. They have all the nice algebraic properties, and they also have all the nice topological properties to cook up nice in various things. That was basically it for today. I have a nice summary on the next page, which we'll discuss. But before, let me just recall what we've seen today. So I showed you a bit about how to beef up diagrammatics using projections and inclusions. I told you a little bit about dimensions, and then about specific dimensions, namely dimension of Hopf-links, basically by taking traces, which gave us the notion of S matrix. And the S matrix is this measure of a category being trivially braided or not. Kind of the degenerate S matrix means basically means there's a trivial braiding, non-degenerate means there's non-trivial braiding. Then I tried to convince you that also classical categories you usually study vector space. Well, vector spaces works, but degraded vector spaces, representation of groups, they are kind of boring. They have a trivial S matrix, but the Valindi categories don't. I showed you a diagrammatic description of the Valindi categories, which I will beef up next time. So I will explain it for any K next time. And in the end, I explained a little bit where the terminology of a modular category comes from. But basically, we are kind of done. So kind of the kind of the best version of a quantum invariant should be now a functor from tangles to modular categories, basically. But let me have just, so here are the exercises, and the exercises are as usual very diagrammatic in nature. So if you want, try to do them. And next time I will construct for you, oh, no, maybe I shouldn't do that. I will construct for you the Valindi categories diagrammatically. But we already have the summary of things we have seen so far. So let me just recall that. So if you want to categorify sets, you get the notion of categories and you have the access to morphism, right? So things without structure give you already morphisms. If you wanted to categorify monoids, then we got the notion of monoidal categories, and we had this access to the two-dimensional calculus, right? Now we could put things next to one another. If you categorify, maybe I should put red dual vector space, it was something, it got a bit tricky. You have different notions. Basically, it's something like rigid, and you got access to to height operations. By what I mean is something like this, right? And zigzags and so on. If you want to categorify braid groups, you got the notion of braided categories, and you got access to the Reidemeister calculus. This was whatever. This is a bad idea, so Reidemeister. Okay, and this was kind of the first part. And in the second part, what I tried to categorify abelian groups. And what I got was this notion of additive abelian categories, and I got access to linear or homological algebra. Right? That's what I did in the sixth lecture. If I want to categorify algebra, then I got the notion of those categories, and I got the in the same way I got the access to homological and linear algebra um, plus two-dimensional calculus plus 2dim, because calc, because it's now it's now this plus this and this. If I wanted to categorify semi-simple algebras, I got the notion of the fusion categories, and basically fusion categories had nice numerics, right? Remember that we had Chur's lemma and matrix categories, and there was a lot of Frobenius-Perron calculations and so on. And the last thing that I just explained is the action of, maybe not green, is the action of the modular group, which gives you those modular categories, and it connects to number theoretical data, because it's a Mobius transformations, and the Mobius transformations turn up in number. So that's what I categorified so far, and that's basically where we end. Not quite. I will still in the next lecture show you how to construct categories of these flavors diagrammatically, but that's at least all I wanted to say for today. So thank you for watching. See you next time.